Well, welcome to the Complex Systems Seminar today. Today we have a really special guest. Our speaker today is Seth Blumsack. And so I'm not going to take too long introducing Seth, but Seth is the John T. Ryan Jr. Fellow, Faculty Fellow, and he's an assistant professor in the Leone Family Department of Energy and Mineral Engineering, as he just said, a department that was recently bought.
Blue light special.
Yeah, exactly. So he's been there at Penn State for about 6 years now, if I'm not mistaken. Before that, he was at a really fabulous educational institution called Carnegie Mellon University with me at the same department. So he got his PhD in 2006. Is that right? A year before I did, in the Department of Engineering and Public Policy, which is this really interesting experiment that takes mostly engineers and tries to teach them the skills of policy analysis. And so his PhD is from Carnegie Mellon University. He has a master's degree in economics also from Carnegie Mellon, from the School of Industrial Administration, and an undergraduate degree in math and economics from Reed University. And so I've never found out whether Seth actually participated in all the crazy things that happened at Reed, but you can ask him about that later. But he's also done a lot of really other sorts of interesting things. For example, he's worked at an economic insight firm in Portland, Oregon that produces really expensive magazines for the energy industry in the Northwest. He's done a wide variety of consulting. He's consulted for the Connecticut Department of Public Utilities Control, for the Maryland Public Service Commission, for the Consortium for Risk Evaluation, and for the American Public Power Association. So he's very well known in the electricity industry as an expert in problems that are associated with the intersection between engineering and economics and policy. His work at Carnegie Mellon is widely cited as helping the electricity industry to understand when particular providers or generators in the electricity industry have market power. And he's done a lot of really interesting work on network topology and how network topology affects electricity systems, particularly on the economic side. And on top of all that, he and his wife run a small hop farm in central Pennsylvania, which is kind of entertaining as well. And so with all that, it's really a pleasure to welcome Seth Blumsack. So let's give him a welcome.
If I'd known you were going to say that, I would have brought a picture. We have all these giant poles sticking out of the ground that I think one day you're going to attract extraterrestrial beings or something like that. But if you ever happen to fly into State College, then you know when you see my house as you're flying in. If you fly in from Philadelphia to State College, you fly right over my house. And so you'll know when you're over my house when you see all the gigantic poles kind of sticking out of the ground. Okay, so I would like to thank Paul for inviting me to come up here. And so what I'm going to talk about today is a sort of strand of research on which I have been working basically for about the past 8 or 9 years. And so I sort of won't be able to cover everything, but I'll at least be able to tell part of the story. And so what has sort of really motivated this is trying to basically use our existing infrastructure in more efficient ways. So kind of basically getting more out of what we already have. And also one of the things that has been kind of bugging me is that related to the smart grid in particular. We still sometimes have great difficulty in communicating what the value of all of these smart grid doohickeys are. So the title of this talk, the rules versus optimization part, I have to give some apologies to Finn Kydland and Ed Prescott, who are a couple of economists from Carnegie Mellon who won the Nobel Prize a couple of years ago. And they won it for some work that they did in the 1970s, basically saying that you should replace the Federal Reserve with a computer, because the Federal Reserve basically has too much decision-making power, which means they're going to do stupid things. So this is not to imply that anything I do is stupid. Okay, so the part of the motivation for this work was starting in the mid to late 1990s. Go ahead. Oh, okay. So starting in the mid to late 1990s, a number of parts of the U.S. experimented with this transition from a very highly regulated electricity industry to one that was much less regulated and much more regionalized. And so, as part of that, there were a number of regional markets for electric generation created. And am I picking up in the mic, or?
It's just.
Is it too loud?
You're good.
I'm good. Okay.
Okay.
Okay. So as part of this broader experiment with the restructuring of the electricity industry, there were these very regional scale markets for electric generation created. And so you have one you have one in New England, and you have one in New York, and one that encompasses the mid-Atlantic. And one of the perhaps unanticipated consequences of this was that the electric transmission system was all of a sudden asked to do some things that it had never been asked to do before. So it had always been there to basically to act as a vehicle for the delivery of a utilities generation to its customers, and now and to do so reliably. And so now what it was being asked to do on top of all of that was to facilitate competition between power generators that were located a really long distance apart from one another. Okay, and so you were basically using this system in ways for which it had not really been designed. And so starting in the early 2000s, one of the things that we noticed was that the cost of delivering power in some areas of these restructured electricity markets began to rise. Okay, not just because of circumstances connected to market manipulation and all these other things, but because but because of increasing strain and congestion on this transmission system. And at the same time, this basically sort of increased the economic costs of the constraints that existed in the transmission system that we maybe didn't really realize were there. The second thing that happened was the frequency of centralized command and control corrective type actions, right? So what we would call transmission loading or transmission line relief actions also started to increase. Okay, and this all sort of came to a head with the blackout in 2003, right? And sort of comments about the state of our electric infrastructure. And so one solution is simply to build more stuff. Okay. And the question that I had sort of started asking was whether building more stuff is always better. Okay. Oh, I did it right. Okay. So I started asking these questions sort of before there was a broad awareness of what exactly the smart grid was, or what it could do for you, or in the case of this picture, what it could do to you. There's, for the smart grid IGERT students in the audience, I want one of your professors to assign to you an old political science article from the 1960s called The Paranoid Style in American Politics. And that article was written basically about the Red Scare, okay? And I think there's a lot of analogies about the public rhetoric regarding the Red Scare and the public rhetoric regarding the smart grid scare, okay? Maybe I'll nominate Paul to do that because then he can wear the smart grid shirt that I made him a couple of years ago. Okay, so I need to be careful with this thing. So my sort of concern is that this is how wide swaths of the American public view the smart grid. Okay? This is, I think, a better but also more difficult description of what the smart grid actually is. Right? So I have this very fancy Swiss Army knife. As you can see, it does all sorts of nice things for me. Okay? And so I got it, and I opened it, and I kind of petted it like a kitten, and then I put it away in a drawer and didn't touch it for 4 months. Okay? But when I needed it, boy, was I glad it was there. And so part of the difficulty in communicating the value of the sort of smart grid architecture, however you want to define it, is that it has this very high option value, okay, or what an economist would call an option value, okay. It's so this sort of option value is something that's very hard to communicate. And so one of the motivations behind some of behind some of this flexible topology work that I'm doing is to try to be able to illustrate what the option value of this network architecture might look like. Okay. What I'm basically going to talk about is, and I'll get basically as far as I can before Paul tells me to be quiet, I'm going to talk about this concept of flexible or adaptive topology control that basically would allow for the co-optimization of the outputs from power generators and the topology of the electric transmission system itself. And so it's not just the output from power generators or their set points that becomes a function of the state of the system. It's also the topology of the system itself. Okay, and so this is a sort of partially a smart grid topic. There are some elements of this type of topology control scheme that you could basically implement now, and to a very limited extent is implemented now. And there are some elements of it where you would need a much more advanced communications and control infrastructure. Okay. So I had basically, oh, there we are. So I have basically three topics in this area to talk about. The first is basically to try to convince you that building more stuff is not always better. Okay, sometimes building more stuff can actually harm system performance. The second is basically a motivation for a couple of approaches I'm taking to solving these flexible topology problems. Okay, so these flexible topology problems are very hard to solve. They're really, in their purest form, they are these very hard sort of mixed integer type control problems. And so the kind of holy grail in this area is finding kind of good heuristics to make the problems easier to solve. And so the last topic is a couple of ideas that I've had recently about basically trying to solve these topology control problems either by basically reducing the size of the problem or effectively finding a way to break the problem up into a whole bunch of subproblems that you could then solve in parallel. Okay. So the first part. So this is basically, this work goes back to some stuff I started back when I was at Carnegie Mellon in the mid-2000s. Okay. And here's sort of the basic kind of toy example. Okay. So, now I have to remember this. This one is, oh, no, I want to use this one. Okay. So this is a simple little parallel toy network. Okay. So you have a source here, and you have another source and a sink over here. Okay. This source here is cheap. This source here is expensive. Okay. And you have basically two parallel paths connecting the source and the sink. Okay? And so basically the optimization problem is to meet all of the demand over here, right, by using your two generators in some cost minimizing fashion. Okay? So you can do this, and basically, depending on what on the electrical properties of these lines, okay, you'll get some amount of transfer on this path and some amount of transfer on this path. Okay. So now I'm going to suppose that you build a line or build a branch connecting these two nodes, right, in this kind of in the kind of Wheatstone bridge type of configuration that you might use to test voltages. Okay, and under certain conditions, okay, when you do that, you actually create a constraint, or well, you don't create a constraint. You hit a constraint in your network. Okay, so you build this line, okay, and you basically create two loops out of one. Okay, and under certain conditions, when you do that, you wind up hitting constraints on certain lines in your system. In the example that I have here, because there is some symmetry in the resistances in this network, when you add this line here, you wind up congesting two other lines. Okay, so you have so in the first example, you had none of the network infrastructure was operating at its rated capacity. You now have two elements that are operating at their rated capacity. And what that means, since this is the transmission system that is constrained here, is that the total power transfer, okay, from this location to this location is actually reduced. Okay, so without the Wheatstone bridge type link, okay, you could transfer 100 units from here to here, and you could do it all using your cheap generator. Right, now that you've added this link, okay, you have reduced the transfer capacity between node 1 here and node 4 over here, okay, by about 8 1/3 units. Okay, and so unless you can reduce demand over here, right, which is not part of the story here. So unless you can reduce demand, you have to make that up with your expensive supply source, right? And so the cost just goes up. Okay, if you did not have a supply source here, then at least according to the rules of this example, right, you would have a blackout, okay, or you would have some unserved load. Okay, so this is a sort of a toy example of a network behavior called Braess Paradox, and the idea behind the paradox itself, basically, that adding links to a network can actually impede the flow of traffic through the network. Right? That idea goes back several decades, right? And so this was first analyzed in the context of traffic flow. Since it's such a neat idea, it has since caught on in all sorts of other applications. So it has been basically analyzed in the context of water, in the context of water pipes. I just published a paper with a petroleum engineering colleague of mine where we outline in all of its gory detail conditions under which you would see this behavior occur for natural gas pipelines. This phenomenon has been studied in packet routing a lot, and even in things like crowd control. And there was actually, somebody told me about a paper just the other day where apparently somebody analyzed what happens to basketball teams when you remove their best player. And in many instances, the team plays better. So I don't know if you can count that, but it's a cool story, so I'm going to count it. So the sort of paradoxical behavior here, in one sense, is not so much a paradox at all, right? This is a little bit different than a traffic network because basically every agent in the network just follows Kirchhoff's laws, as opposed to in a traffic network where you have individuals that are making some sort of time or other cost minimizing routing decision or something like that. Okay, I sort of spent a lot of time early in my career, again outlining in some gory detail conditions under which you would expect to see this paradoxical behavior occur in circuits. And then a sort of couple of other folks, Emily Fisher, who is now at Berkeley Lab, and Corey Hedman, who is now at Arizona State, basically took this sort of observation and said, well, if you can improve flow through the system, okay, by removing lines, then why don't we just schedule lines based on the state of the system? Okay, and so they sort of had this idea of scheduling transmission lines to try to minimize congestion. Okay, so that's sort of one way that sort of you can deal with this. There was a pretty interesting paper that came out last year from Anna Nagurney, who's now I think is at the University of Massachusetts, and she basically shows under certain conditions that the paradox is self-correcting. Right, basically, if you get enough individual agents trying to make routing decisions through a network, right, eventually they will figure out that their decisions are not that smart, and they will effectively change their minds. And this sort of self-correcting behavior doesn't really work in not just in power grids, but basically in any network that where you would basically describe it using Kirchhoff's law. So the same thing, the same sort of behavior would not really apply to a gas network, for instance. Okay, if you want to avoid this paradox in network design, it's not just a matter of how much traffic you push through the system, right? It's a matter of basically choosing your network design parameters in some way that's smart. So just to sort of give you an example, for the very tiny network that I showed you before, what this picture basically shows is the flows on certain links in the network. So this is the flow on the bridge, and these are the flows on the other lines. Okay, as a function of the susceptance of the bridge. Okay, so as you increase the susceptance of the bridge, then you're going to get more flow on the bridge, and the flow on the boundary lines are going to get reallocated. And at some point, okay, you basically hit the point where you have a constraint, or where you hit a constraint, right, on a couple of your boundary links. Okay, and so you can, if you're smart enough, you can choose if you're smart enough, you could choose the electrical parameters of your network to try to avoid this behavior. Another option is that you could constrain flow on certain links to avoid this behavior. For example, what this basically shows you is the combinations of the susceptance on the bridge and the maximum allowable flow, so the path rating on one of the boundary links. Okay, so it shows you basically the set of points where you will all of a sudden move from the uncongested state to the congested state. Okay. So in the sort of little model that I just showed you, you could choose your parameters wisely, I guess, to avoid this behavior. In larger networks, that's sort of a little more difficult. But this sort of does. I mean, having to basically do all this analysis does sort of beg the question as to, if the network was working perfectly fine before, okay, why on earth would you build the bridge? Okay. What I did was basically, this is the 118 bus network, the sort of standard IEEE 118 bus network. And what I did was I identified a bunch of different subgraphs. Okay, a few of them are just in these red circles here that topologically look like my little Wheatstone bridge. Okay, And so what I did was basically to conduct these experiments where I simulated a bunch of load profiles on this network, okay, with and without the bridges in each of these little Wheatstone subnetworks. Okay. And so for these three, okay, when you remove the bridge, you do reduce congestion in the network. Okay, so you lower the total cost of meeting all of the demand in the system. Okay, but your system is no longer what we would call n-2 secure. Okay, in the sense that if you take the bridge out and then you take another line out, then you could have a situation where you would not be able to meet all of the demand in the system. Okay, so that happens in these three places. And so why on earth would you ever have this sort of topology in your network if it's so troublesome? Well, I mean, in this case, you could argue that it is basically the price of having a secure system. Okay, this is not to say that there is not some other line you could have built, okay, which would have given you that same level of security. Okay. This sort of trade-off, okay, between having a system that doesn't run perfectly and efficiently during normal conditions, but continues to run, or it continues to run in the case of a contingency, that's not, I mean, that's sort of cool, but it's not something that is universal by any means. And so just as an example, if we take this little Wheatstone bridge type topology over here, and we all of a sudden remove the bridge link, then the system is still what we would call n-2 secure. Okay, so there may be, you know, there may be some sort of redundancy value, okay, to building these topologies that under normal circumstances or under normal operating conditions don't seem to, or would seem to increase cost and make the system run less efficiently. Okay, and so the idea behind the topology control literature, okay, a lot of which basically built out of this work that I did in the mid-2000s. The basic idea behind this is that, well, why don't we, I mean, using the sort of simple system that I showed you in the beginning, okay, why not basically open the circuit to the bridge, okay, but close the circuit when we need it, okay? And so you could play very sort of targeted games like that. More broadly, okay, so if you want to play targeted games like that, that in really complex systems can be a very difficult thing to do because you basically have to go through the system and find all the little topologies of interest. So you have to solve this like subgraph matching type of problem, right? And those are not that easy to solve. I thought I had done something really, really slick in my dissertation, and if anybody wants to go back and actually look at it, you can see where what I did was actually not so slick after all, because you still wind up having to kind of search the entire topology space, okay, to find what you're looking for. So instead of doing that, instead of trying to target certain topologies, right, which may work, the alternative would be to simply co-optimize the system topology, okay, along with your set of generator outputs. Okay, so you want to basically co-optimize all of the stuff in your system. And there's a few ways to go about doing this. One way, which I am just going to mention here that I'm not going to talk about very much, is basically through power electronics or fax devices that could do things like effectively adjust the reactance or the impedance on different links. Okay, and so you could adjust the impedance by some small amount that could effectively create more transfer capacity between a couple of points. Okay, and so this is, you could do this either through centralized control, or you could do it through more distributed decision making. A student of mine that actually just graduated and is now actually working with Corey Hedman at Arizona State has found that under some conditions, those distributed topology control conditions, okay, would be basically the same solution you would get if you had some centralized entity optimizing the whole system. So I don't want to read too much into this, but that's kind of interesting, and that's something that we're continuing to work on. Okay. What I am going to talk about more is the kind of discrete version of that, which now I guess has been is now either called optimal transmission switching, or sort of I like to call it flexible topology control. And so the idea is that instead of continuously adjusting line parameters, you basically have on-off switches. Okay, so you have fast relays or something like that. And so the work that has been done on this, okay, suggests that if you could figure out how to implement this type of co-optimization or some way of making the network topology more adaptive to the state of the system, then you could increase the economic efficiency with which the system operates, and in some cases, you would leave the system just as secure as it was prior to the topology modification. Okay. But the problem, of course, is that actually solving these problems is very difficult. Okay. So I'm going to use this. I'm going to use this term optimal transmission switching, and so I want to talk about exactly what I mean when I say this. Okay, and so basically, what you do is you take your kind of optimal power flow, okay, type of problem formulation. Okay, so this is the linearized DC optimal power flow, which minimizes generation cost. That's what's in the objective here, subject to like a whole bunch of constraints, of system constraints and Kirchhoff's laws. And in here, I have added some of what we call unit commitment constraints. So these are things like the timing of when certain generators are turned on and off. Okay, and so what you do to this problem, so this is basically the linearized DC optimal power flow problem with unit commitment constraints. And then what you add to that to magically transform it into the optimal transmission switching problem is you add another set of indicator variables that are also decision variables for the state of the line. So whether the circuit is open or closed. Okay, and so this is the problem that's difficult to solve even in the linear DC case. Okay, so so this problem has been solved, and I'll qualify what I mean about that in a minute. So this problem has been solved for a number of different kind of standard IEEE test networks, and in most cases, whoever solves the problem finds that in fact you could actually use the transmission system more efficiently, right, if you were to co-optimize its topology along with generation. So for the what's called the RTS 96 test system, the folks that originally did this analysis claim to have solved this problem to optimality basically by brute force. Okay, which they had on a fast computer, so I guess they could do that. And so basically for every dispatch period, so for every for every decision about the optimal generator set points and network topology that you have to make, on a system that is not very big, it took more than 20 hours to solve this problem. Okay, and so that sort of gives you an idea. And for bigger systems, you can demonstrate that your solution is at some local optimum, but they're basically, I don't think anybody's ever claiming that the solution to the optimal transmission switching problem is actually optimal. Okay, so if you actually wanted to try to do this, right, on a real system, you need a better way to solve these problems. And so what we did, so when we started thinking about this, the first thing that we did was we managed to get the solutions to the optimal transmission switching problem on this network for 24 periods. So this might correspond to like 24 hours of dispatch or something like that. Okay. And so we got all of the data, and we looked at which lines were actually switched on and off at which times. Okay. So I'll sort of explain what you're watching while you're watching it. And it's a little bit dark, but the left side here is basically this RTS 96 system with no transmission switching whatsoever. You just basically dispatch it with the topology you have, so you adjust generator outputs. And this system over here is the same RTS 96 system, but with optimal transmission line dispatch in addition to optimal generator dispatch. And so the stars represent generators. The little little circles here represent demand. And the size of, the little boxes represent demand. And the size of the star, right, shows you the amount, the relative amount of electricity that that each generator is producing, and the shading that you see that varies by location shows what the location-specific price of electric energy is. So basically, that's the marginal cost of delivering electricity to a specific location. So light is really expensive and dark is really cheap. Okay. So we looked. So we what we were looking for basically was something that we were basically looking for two things. Okay. First, the second thing that they teach you in any introductory economics class is that there's diminishing returns to everything. Okay. So so what we were looking for was some evidence of diminishing returns to the flexibility of the network. So is there some point where you might switch lines on and off, but it doesn't do very much for you, right, in terms of your economic objective? And the other thing that we were looking for was whether there were any, whether there was anything that might be a good predictor, okay, of whether you would want to switch a line on or off in a certain period. Okay, so what we did was we took all of the results from this from this optimal transmission switching analysis, and what we did was we basically calculated the incremental value, right, in terms of the economic objective from switching lines on and off. Okay, and what we basically hypothesized, okay, was that as you include more lines in your set of lines that you switch on or off, okay, then the incremental benefit of including another line in that set is always decreasing. Okay, now that to me seemed perfectly obvious, right? And part of the reason that it seemed perfectly obvious is that if you look at the supply curve, okay, which tells you the cost of meeting demand for different levels of demand, okay, the supply curve for electricity systems typically has a shape like this. So this is the supply curve for the PJM electricity system, okay? So basically over some very broad range of demand, okay, the marginal cost of meeting electricity is basically flat. So the incremental cost of meeting demand when you have 60,000 megawatts is basically the same as 100,000 megawatts. Okay? But as soon as you get to some point, all of a sudden that cost starts to increase really, really fast. Okay? If any of you are looking for trivia, for cocktail parties in the industry, this is called the devil's elbow. Okay? And this is a characteristic not just of electricity supply curves, but supply curves for basically almost any energy commodity. So you see this behavior in natural gas, and you see it in oil. Okay, so because you have this really steep part of the supply curve, okay, what you would basically expect is that as you keep removing lines from the system, okay, as long as those lines relieve congestion, what you will basically be doing is using less of this stuff, this expensive stuff, and more of this inexpensive stuff. And at some point, you will stop using all of the expensive stuff. Okay, so that's sort of the intuition. But exactly where that kicks in is a little bit difficult to determine. Okay, so we were also basically did some poking around, trying to see if there were any kind of network characteristics, okay, that would basically be good predictors of whether lines were switched on or off, right, in this co-optimization problem. And I can show you as many pictures as you want, but basically we didn't find any. Okay, so here are some pictures that are not very interesting. So this one is more interesting. Okay, so basically what you have here is the result of all of this incremental analysis. Okay, so on the columns of this matrix here are the different dispatch periods, and the rows indicate different lines that they're just indicator numbers for different lines that are switched in different periods. Okay, and so if you see a number in a box, okay, in an entry of this matrix, it means that that line was switched off during that period. Okay, and so the numbers in the boxes indicate the reduction in cost associated with removing a specific line from service during a specific load period. Okay, and so the green boxes indicate the lines that the optimal transmission switching algorithm said you should remove from service, but in fact don't give you very much in terms of economic benefit. The red boxes, so there's these two sets of red boxes, those are the sets of lines that the optimal transmission switching algorithm says that you should remove from service and actually do contribute relatively substantially to reducing cost. Okay, so basically what we got out of this was that there were a few, so over the course of this 24-hour period, there were a few dozen lines that the algorithm said you should switch off at one point or another. But what we found was basically that there were basically only two of those lines, this one here, this one that says 309, 311, and this one up here that says 109, 111, that actually contributed substantially in any way to a reduction in the cost of meeting demand. Okay, so what this says is that at least for this particular network, these diminishing returns okay, to flexibility in the network topology set in very fast. Okay, because so if you were to basically just consider these two lines, okay, you would get the vast majority of the economic benefit, okay, with a lot lower computational time to solve the problem. So that we expected. Okay, what we didn't expect was that these incremental contributions are almost, but not quite exactly, additively separable. Okay? So what this shows you is that for each of the 24 load periods, what we did was we calculated the incremental value of switching each line off individually and added them up. And we compared that to the cost reduction that you got from switching off all n of those lines jointly. Okay? And the differences here are in percentage terms. So the biggest percentage difference that we saw, okay, between the sum of the incremental contribution to dispatch cost savings and the joint contribution to dispatch cost savings was about 0.15%. Okay, so what we basically got out of this exercise was one result and one motivation for trying to find ways to reduce the size of these adaptive topology problems. One motivation that we totally expected, and one that we were actually a little bit surprised at. Okay, so what we basically found was, basically there are substantial diminishing returns, and that the effects of this line switching, this topology control, are more localized than we actually had expected. Okay. So how much time do you want me to leave for questions at the end? At least 5 minutes. Okay. Okay. So where this basically landed us was a couple of different approaches for trying to solve these problems more quickly. Okay. And so this is I'll talk about this stuff pretty briefly. Okay. So one is basically the idea that is you simply reduce the solution space. Okay. So you have some heuristic or some rule that tells you whether or not you want to include a line in the set of lines that you would consider switching on or off. Okay. And then the second one is that since we found that the effects of switching out transmission lines were almost additively separable and two fairly localized, okay, it seemed reasonable that another way to proceed with solving this problem would be to basically take the system and break it up into a bunch of subsystems and then solve the problem on each of those subsystems. Okay, and so what we were basically trying to figure out is, what sort of heuristic screen would be useful, okay, for simply trying to reduce the size of the system-wide topology control problem. So what we found was basically that that there are some graph metrics that are actually very useful for the parallelization problem, but not so much for the screening problem. So, so basically the screen we used was basically based on a set of network sensitivities that describes how that basically describes how flow reallocates itself, okay, when you remove a branch element from the network. Okay. And so the sort of punchline for that is that this sort of sensitivity-based screen, okay, gives you so the red line here is the sensitivity-based screen. The green line at the top, okay, is the cost savings from the optimal solution. Okay, and so what we did was we basically we ranked lines according to this screen, okay, and then solved this optimal transmission switching problem with a different number of lines in the set of candidate lines. And so basically, if you rank lines according to the sensitivity screen, once you get to about 6 or 7 lines in the candidate set, okay, versus 70 some odd lines, right, then you can get basically the optimal solution, okay, and the bottom piece here shows you the amount of time that it takes. So solving the full-blown optimization problem for the whole system is this green line here. The time using our sensitivity screen is the red line. And so you can reduce the time it takes by around an order of magnitude, or in some cases more. So we've done this for this RTS 96 system, and we have done it for a number of other systems. The parallelization is something that we're still working on, but that seems to, at least for some of these systems, work just as well as this screen. So this sort of topology control area, or this adaptive network area, is the battery fell out of the mic. Should I try to put it back in?
It's fine.
You can hear fine. Okay. I'm just about done anyway. Okay. So this is an area that is in the power systems world. This is a pretty active area of research now because it's kind of a cool new problem. I'll just hold on. So there are a few kind of like grand challenges remaining. Okay, at least at this point. One is that we're basically solving all these. We're basically solving these topology problems in a very linear world, and then if you expect them to work just fine, when you plop them into this very nonlinear system, you're probably fooling yourself. Okay, and so the question is, the solutions that you get in the linear world, are they worth anything, right? And so one of the things that I've been thinking about is finding ways to try to correct the linear solutions for the nonlinear world. Sort of another question is that if you wind up opening and closing these circuits really fast, what sorts of dynamic problems do you introduce? And then if you actually tried to do this, right, what exactly would you need, right? So if you were to effectively reduce the impedance of a line to 0 really fast, right? If you had a protective relay or something that had an impedance setting, would you have to somehow have some way of telling the relay that no, we really did mean to do this and nothing is wrong? So with that, I'm happy to take questions, and that's it.